shining a light on the unknown. Breakthroughs in ultrafast electron dynamics. When electrons move within a molecule or semiconductor, this occurs on unimaginably short time scales. A Swedish-German research team including physicist Dr. Jan Vogelsing from the University of Oldenburg has now made significant progress towards a better understanding of these ultrafast processes. The researchers were able to track the dynamics of electrons released from the surface of zinc oxide crystals using laser pulses with spatial resolution in the nanometer range and at previously unattained temporal resolution. Advancements in electron behavior research. With these experiments, the team demonstrated the applicability of a method that could be used to better understand the behavior of electrons in nanomaterials and new types of solar cells, among other applications. Researchers from Lund University, including Professor Dr. Anne Lullier, one of last year's 3 Nobel laureates in physics, were involved in the study, which was published in the science journal Advanced Physics Research. In their experiments, the research team combined a special type of electron microscopy known as photoemission electron microscopy, PEEM, with attosecond physics technology. The scientists use extremely short duration light pulses to excite electrons and record their subsequent behavior. The process is much like a flash capturing a fast movement in photography, Vogelsing explained. An attosecond is incredibly short, just a billionth of a second. Combining advanced techniques for improved accuracy. As the team reports, similar experiments had so far failed to attain the temporal accuracy required to track the electron's motion. The tiny elementary particles whiz around much faster than the larger and heavier atomic nuclei. In the present study, however, the scientists were able to combine the two technologically demanding techniques, photoemission electron microscopy and attosecond microscopy, without compromising either the spatial or temporal resolution. We have now finally reached the point where we can use attosecond pulses to investigate in detail the interaction of light and matter at the atomic level and in nanostructures, said Vogelsing. Technological breakthroughs and future research. One factor that made this progress possible was the use of a light source that generates a particularly high quantity of attosecond flashes per second, in this case, 200,000 light pulses per second. Each flash released on average 1 electron from the surface of the crystal, allowing the researchers to study their behavior without them influencing each other. The more pulses per second you generate, the easier it is to extract a small measurement signal from a dataset, explained the physicist. Anne Lullier's laboratory at Lund University, Sweden, where the experiments for the present study were carried out, is one of the few research laboratories worldwide with the technological equipment required for such experiments. Vogelsing, who was a postdoctoral researcher at Lund University from 2017 to 2020, is currently in the process of setting up a similar experimental laboratory at the University of Oldenburg. In the future, the two teams plan to continue their investigations and explore the behavior of electrons in various materials and nanostructures.